Hello, my name is Rohan-Paul and very welcome to my computer vision and deep learning YouTube channel. Let's get started. Hey everyone, so this video is about the DCGANs generator function and what kind of input shape or kernel size or number of filters it takes. So to give the background, a while back I made a video on implementing DCGAN with TensorFlow, and then I received quite a few questions both in the YouTube comment and also in my other social media account about why the particular input shape that I took in that project, what was the reason of taking that particular number, or the filter size or the kernel size, the number of input dimension, etc. So I thought to make a separate video altogether just focusing on this topic, because this is such an important aspect to build any GAN network, or for that matter any computer vision deep learning project, because all these parameters, that is filter size, a kernel size, number of filters, then number of input dimension or the number of neurons at the various layers, these are all hyperparameters and you have to tune it. There is no perfectly valid answer what's the best optimal number that should be. There is no mathematically or analytically derivable number for these parameters. All these are based on your understanding and also some bit of experimentation, that what kind of input shape or what kind of kernel size gives the best result for your model. So understanding it is of immense importance. All right, with that intro, let's get started. First, a quick recap of the GAN architecture. So GAN contains two networks which has two competing objectives. The first one is generator and the second one is discriminator. And the generator generates new data instances that are similar to the training data. In our case, the training data is celeb A images. So the only purpose of generator is to take a latent noise vector as a starting point and create images which are almost equal to the original celeb A images. And now coming to the discriminator evaluates the authenticity of those provided images, that is of all the images that the generator created. So the discriminator classifies the images from the generator and the original images, and it outputs a probability estimate ranging between 0 and 1. That is, if the discriminator thinks an image is not fake, that is an image is true or real, then the probability should be close to 1. Otherwise, if the discriminator thinks that it's a fake image, then the probability should be close to 0. So this is the that min max formula, and as it shows, the generator optimizes for maximally confusing the discriminator by trying to make it output high probabilities for fake data sample. On the contrary, the discriminator tries to become better at distinguishing samples coming from G from samples coming from real distribution. So the GAN training process consists of a two-player mini-max game in which the discriminator is adapted to minimize the discrimination error between real and generated samples, and the generator is adapted to maximize the probability of D making a mistake. When G does a good enough job to fool D, the output probability should be close to 1. And now a quick recap on the regular convolutional neural network. So in CNN, convolutions are performed by sliding one or more filters over the input layer. Each filter has a relatively small receptive field, that is width and height, but always extends through the entire depth of the input volume. At every step, as it slides across the input, each filter outputs a single activation value, which is a dot product between the input values and the filter entries. So that was a regular CNN, and but in DCGAN I have to understand something called transposed convolution, which is something like the opposite of this regular convolution. So let's take a look at that. So this image is taken from the famous paper on DCGAN. This particular image was shown in that paper. So in the generator part of these DCGAN architecture, I need to implement these transposed convolution, and what it is that under the transposed convolution, we reverse the process. Instead of taking an image and processing it into a vector, we take a vector and upsample it to an image. So if you look at this image, we start with the single vector, which is a 100-dimensional input vector, also called the noise latent vector, and then upsample with each layer, and ultimately giving me this wide layer at the end. So that's a generator. So basically, for the generator, convolutions are replaced with up convolution. So the representation at each layer of the generator is actually successively larger as it maps from a low dimensional latent vector onto a high dimensional image. So just the overall architecture is something like this. The generator takes in some noise, which is this 100 vector noise vector, and then it uses transposed convolution to upscale the image to 1024 channels, and then 4x4. Then it upscales again to 512 channels with 8x8, and it goes on doing that until it obtains 64x64 and then 3x3 RGB channels. But that was a generator, and note the discriminator part of the architecture is just like a normal convolution. That is, we start with these larger tensor, and with each layer we successively downsample it to come to this ending layer. And coming back to the code, this is my notebook that I built in the previous video for doing the entire DCGAN architecture from scratch. Now in this video, I am only going to, like I said in the first part, that I'm only going to discuss the generator function and how exactly I am deciding on the input shape, kernel size, and number of filters, etc. So before going into the detail, just a quick recap of this notebook, that initially I'm just importing the celeb-A dataset, which is I'm importing it from Kaggle, and then I am having a generator function here. This is my generator model, and the only purpose of this generator model is that given a input noise vector of shape 100, the generator model will generate images which are almost equivalent to the original celeb-A dataset, or as close as possible. And then I will also have a discriminator model. Here is my discriminator function. That the purpose of this discriminator function is to decide whether an image given to it is fake or the real image. That is, whether it can decide that the image was generated by the generator model or it came from the original training batch of celeb-A. And so that was my generator model, and final DCGAN training. Here I am actually training it. So here, for the sake of to be within the limit of within my machine's GPU power, I only ran a batch of, I think, 50 or so, epochs of 50 or so, batch of 64, and that started generating some celeb-A faces. But of course, DCGAN is a superb GPU intensive process, and it will take really a lot of power. And so probably if I run 100 and 120, what I did in Kaggle, inside the Kaggle kernel, then I was getting almost realistic images close to celeb-A. So anyway, coming back to my generator function, the whole point of discussion in this video. Yeah, let's stop here. Okay, so let's start with the generator model step by step. So what I'm doing here, first I'm initiating a sequential model of Keras, then I'm adding a dense layer with 4x4x512 as the unit number of units, which is the first parameter of dense method of Keras. As you can see in this official documentation that is coming here, dense, the first parameter is units, and activation equal to none, because I do not have any activation here, and kernel initializer, all these things I'm not passing. All right, and then the input shape. The input shape, normally you have to pass the input shape of your input images. In this case, in the case of DCGAN, remember that we are always starting with a 100 element noise vector, which is my noise shape defined here, and that's exactly you have to pass here, because the whole architecture is starting with this noise shape, and then gradually it will build a full image out of this. So this is my starting line, and then I'm adding a reshape layer to the network to reshape the tensor from the last layer of the last layer to a tensor of shape 4 by 4 by 512. And the next I'm adding a conv 2D transpose. This is that famous function of TensorFlow Keras, where it's implementing the transposed convolution that we discussed in the first part of this video. And what the official documentation is saying, the need for transposed convolutions generally arises from the desire to use transformation going in the opposite direction of a normal convolution. That's exactly what he talked about. When using this layer as the first layer in a model, provide the keyword argument input shape. All right, and okay, so the transposed layer, first parameter it takes is number of filters, which is an integer, and this is actually the dimensionality of the output shape, that is the number of output filters in the convolution. And then the second parameter is kernel size, or this is sometimes also called filter size, an integer or tuple of two integers specifying the height and width of the 2D convolution window. Can be a single integer to specify the same value for all spatial dimension. Okay, so to my conv 2D transpose, initially I'm passing 256 as a number of filters, and then the filter size or the kernel size I'm mentioning is at 4. Normally 4 means it's a square filter or square matrix of shape 4 by 4. And then strides I'm passing 2. It will actually double the number of double the shape in my next layer, and padding keeping it at same. All right, that's my first conv 2D transpose, and then I'm applying batch normalization, then leaky ReLU with alpha of 0.2. So that is kind of one set of actions. Then comes my second conv 2D, and here again I am giving the filter as 128, half of 256. Kernel size, strides, and padding remains exactly like the previous one. And then again leaky ReLU, batch normalization. And this is my third 1, 2, 3. Yeah, this is my third conv 2D, where I have the filter at 64, kernel size, strides remain same. And then again leaky ReLU and batch normalization. And this is my fourth and final conv 2D, where I am passing filter size 3, kernel size 4. All the rest of this remains same. Here only difference is this is a last layer, so I'm passing a sigmoid, activation of sigmoid. And finally I'm returning these generator model from this function. And then I'm printing generator.shape, I'm actually invoking, executing this function generator model, and then I am printing the summary of it. Now let's start understanding some of the key parts of this function. So the first one is this unit parameter given to the dense method. So this first parameter unit is actually is positive number, and it represents the dimensionality of the output space, and it has to be, obviously it has to be a positive integer since it represents the dimensionality of the output vector. And the units of each layer will define the output shape, that is the shape of the tensor that is produced by the layer, and that will be the input to the next layer. And each type of layer works in a particular way. For example, the dense layer, for the case of dense layer, the output shape is based on this number, which is a unit. But for example, in the case of transposed convolution layer or even convolution layer, the output shape will depend on the first parameter, which is filter. Here, for example, I'm giving 256. Now let's check out the summary. When I printed the summary for the after the first dense layer, I got total number of parameters as 827392. Let's see if we manually calculate it matches. Before calculating, let's check what the dense layer is taking. It's taking 4, 4, 5, 1, 2, and the input shape is a noise shape, which is 100. Which means I'm applying each one of these 512 dense neurons to each of the 4 by 4 kernel size to the 100 element noise vector. So my calculation would be for the total number of parameters here would be let's define a variable a equal to. So first I have to calculate the number of parameters in here, that is whole 4 into 4 into 512 multiplied by 100. 4 into 4 into 512 into 100, and to this I also have to add the bias term, and that would be just 512 into 4 into 4. And now if I print a, let's see what I get. All right, it is giving me 827,392 is the total number of parameters, 827,392, and that's exactly what I'm getting here as well, 827,392. So that's the total number of parameters, and we just saw that how it's calculated. So now what this means is that these DANs is pretty much Keras's way of saying about matrix multiplication. So as a separate example, so what here it did is just a clear matrix multiplication between two vector, between one, in this case one tensor and one vector. So for example, just as an example, whenever I take a normal, in the normal case, here it was a little special case because I had the input shape of 100 vector, but in a normal case mostly you will be using, when applying DENS on a set of training images, you will be using something like this. That is, for example, DENS I am passing 512 as the number of units, so the number of neurons. Activation, for example, ReLU. Input shape is some standard input shape I'm taking here, which is 32 by 32 by 3. That is 32 height, width, and 3 channels for a color image. What we are really saying is to perform a matrix multiplication to result in an output matrix with a desired last dimension to be 512. And then coming to the next function, which is conv2d transpose, that will implement my transposed convolution on the input vector. So here again, the first parameter 256 is a number of filters, and this is an integer which is the dimensionality of the output space, that is the number of output filters in the convolution. And this number of filters is actually the number of neurons, and each neuron performs a different convolution on the input to the layer. And then the next parameter to conv2d transpose is kernel size. So this kernel size, first check the signature, how you have to pass this number to kernel size. If you pass just 4, that means it's a 4 by 4 kernel, assuming it's a square, because mostly it is a square. And otherwise you can pass something like this. Let's comment out. For example, if you pass a kernel size 3 and then a multiplication sign and then 3, this is actually equivalent to 9,9. So you have to be careful on this. So if you, instead of comma, if you pass it like this, 3 multiplied by 3, then the kernel that will be applied, that is a filter that will be applied, each of those filter size will be 9 by 9 and not 3 by 3. So it has 81, that means it will be having 81 trainable parameters for the 9 by 9 kernel and 1 bias. And take another example. Let's say if you pass something like 2 by 2, 2 multiplied by 2, it will be equivalent to 4 and 4. So if you actually want to pass a 2 by 2 and not 4 by 4, then you have to do something like this, just with a comma, 2, comma 2. So otherwise, if you do this like this without the comma part, it will mean 4 by 4, and it will have 17 trainable parameters. That is 16 for kernel, 16 for kernel of size 4 by 4 plus 1 bias one. All right. And now somebody can ask obvious question that comes to the mind, that what is the most optimal number to choose for your kernel size or filter size? And the answer, simple answer, is there is no optimal size. The most popular choice that is used by almost every deep learning practitioner is 3 by 3 kernel size, but it is ultimately a hyperparameter, and you have to tune it and you have to see what's really best for your model. But there's a rule of thumb, and that rule of thumb is this. One second. Yes, that rule of thumb is this, that if your input image is larger than 128 by 128, consider using a 5 by 5 or 7 by 7 kernel to learn larger features. Else, if your images are smaller than 128 by 128, you may want to consider starting with a strictly 3 by 3 or 4 by 4 kernel size. And similarly, coming back to the question on number of filters to conv2D transpose, which we just said that it is actually the number of neurons. So again, the same question may ask, you may ask that what's the optimal size for deciding on the number of filters? And the question remains the same, that it's a hyperparameter. There is no perfect number for every model. It depends on the situation, on the data set, on your particular target, etc. And here I am giving a number of 256 to my first conv2D transpose. What it actually means is that the model will learn a total of 256 filters in this layer. Now, let's take another example. Let's say that I want to generate images and my input images are of dimension 200 by 200, and I want to apply a DCGAN on this training set of images which are of shape 200 by 200. So that means the final shape of the images generated by the generator model should also be of shape 200 by 200. And let's say for the dense layer, I'm starting with the shape of 25 by 25 by 450 or something. Let's actually code input the. I'm just inputting the code that I have already left somewhere. Yes. Okay, so this is the situation that I have the input images of 200 by 200, but and I am assuming that that I want to start with a dense layer of 25 by 25 by 432. So that means to get to the number of 200 by the end of the generator model, I have to deconv the number 3 times. That is 25 multiplied by 25 multiplied by 2 by then another 2 and another 2, which will give me the number 200. And that's exactly this model here in this architecture is doing. That is, a first conv2D is here, second conv2D is here, and the third conv2D is here. So by the end of this 3 up convolution or transpose convolution, I will have the final input shape of the generated images also 200 by 200. In my case, that is in this case in the generator model, my original image shape of the celeb A dataset was 64 by 64 and 3. That is 3 channels, and I started with 4 by 4. That means to get to the number of 64, starting with 4, I had to apply conv2D 4 times. Why? Just something like this. That is 4 multiplied by 2 into 2 into 2 into 2. This will give you 64. And how these 2 is coming, because I'm using a strides of 2. It will, for each layer, it will double the shape with a stride of 2 in the case of transpose convolution. But just in the opposite case, that is, instead of conv2D transpose, if you are using just conv2D and you are using strides of 2, it will half your input shape. That is, in each layer you have a stride of 2 for conv2D. The output layer will have half the size of the input shape. And as a separate point here, remember a very important thing, that when using strided convolution, that is your strides, like for example here I'm using a strides of 2 for all my layers. So when using strided transposed convolution, in order to avoid checkered board artifacts effects, which is caused by unequal coverage of the pixel space, kernel size should be divisible by its number of strides. That is, here my kernel size is 4, my strides is 2. So 4 is divisible, perfectly divisible by 2. You have to make sure of that, otherwise you will get the very infamous checkered board artifacts effects in your output images. And the main cause of this is uneven overlap at some parts of the image, causing artifacts. These are normally regularly fixed by this rule that I just mentioned, that kernel size should be perfectly divisible by strides number. Now let's quickly talk about the concept of filters versus filter size, or kernel versus kernel size. Now each convolution layer consists of several convolution channels, also known as depth. And in practice, they are a number such as 64, 128, 256, 512, etc. For example, in this notebook for the generator function in DCGAN, at the input dense layer, I took this number, that is the number of channels, to be 512, and this is also the number of filters, which is the first parameter to conv2d transpose function. So this is equal to the number of channels in the output of a convolution layer, and that was the number of filters. Now coming back to the concept of kernel size or filter size, this on the other hand is the size of these convolution filters. So in practice they take values such as 3 by 3, 1 by 1, 5 by 5, or even sometimes 7 by 7 for larger images. And in abbreviated form, this kernel size is sometimes written as just, for example, for 3 by 3 I can write just 3, and for 5 by 5 I can just write 5. And for example, this notebook, I took the filter size to be 4 by 4, or I actually included the number just 4 in the code. So this is, let's take an example. So this is that image. In the below image, I am presenting a normal convolution, and this is my input image, 12 by 12 by 3 channels. And after going through a 5 by 5 by 3 filter or kernel, this 12 by 12 by 3 image will become a 8 by 8 by 1 image. You can do the math and get this number. So here the number of filter is just 1, and the filter size, that is a kernel size, is 5 by 5 by 3. Now what if I want to increase the number of channels in my output image? What if I want to output an image of size 8 by 8 by 256? Well, I can just create 256 kernels or 256 filters to create to create this 256 of these output images. So let's see the next image. So this is what I'm talking about. Now I am taking the same input image of 12 by 12 by 3, and my kernel size also remains the same, which is 5 by 5 by 3, but I am including a dimension of 256 to create this output shape, where my output shape has a depth of 256 or a channel of 256. So this is how a normal convolution works, and here the filter size 5 by 5 by 3 by 256 represent the height, width, number of input channels, and number of output channels of the kernel. And that's what I included in my conv2d function. Let's quickly take a look at that in my original code. So this is a notebook in my original code for implementing this generator model in my DCGAN. And here for the dense layer, I am selecting the shape 4 by 4 by 512, and let's take a look at this conv2d transpose. This is where I mentioned the number of filters and the concept that we just discussed. And the kernel size I'm mentioning as 4. So what it does is these 256 will be the output shape or output number of channels from this conv2d transpose layer. That's what it does. And kernel size I'm mentioning as 4. And again, if you ask the obvious question that what is the ideal number of filters to be given in a conv2D transpose or to conv2D in a CNN, and the short answer is there is no direct method to know this number. It's an hyperparameter. You're supposed to tune it to get your best number. However, you can test some common values like 16, 32, 64, 128, 256, 512, etc. And if you want to go into the detail on this concept, that what's the ideal number or what could be the best number I can take, first note that the first parameter, this filter to conv2D, this number 256 here, this is the dimensionality of the output space, that is the number of output filters in the convolution. That is the image that will be the output from this layer, that will have a 256 channels or 256 depth. So the number of filters is actually the number of neurons in the neural network, since each neuron performs a different convolution on the input to the layer. In general, people tend to use power of 2 for different hyperparameters in neural nets. For example, you can see all these numbers like 16, 32, 64, 128, 256, 512, all these are power of 2. And it is not definitively proven to be more effective, but there are schools of thought that point to it being the most effective approach. In terms of the number of filters, filters are meant to detect features. If you add more filters, it should be able to capture more complex features, whether they be visual or physical. The drawback to increasing the number of filters, though, that in each layer, the added parameter that are associated with it, and that will actually makes your model take up more memory, and it will take longer to train as there are more parameters to update. So again, in general, the more the features you want to capture and potentially available in an image, the higher the number of filters required in a CNN. So the more the number of filters, the more the network learns. But this is not necessarily good all the time, because saturation and convergence matter the most. So in another word, the number of filters that you set in a layer is to allow enough containers to network to learn relevant features or their combination. And what is the sufficient number depends upon the dataset. Say a CNN network at layer X needs at least 24 feature maps to learn important feature. So you provide, say, 32, working on the idea that you give the network a little bit of breathing space, little bit of leg room, and let it decide on its own. Maybe some of those 32 are redundant or slightly varied, but you just give a little bit more than the absolute minimum required for these number of filters. And finally, let's wrap up and summarize all the things that I'm doing in these generator function of my DCGAN model. So first, noting again that we already discussed that the regular convolution is typically used to reduce input width and input height while increasing the depth. Transposed convolution, on the other hand, goes in the reverse direction. Here, we are going to increase the width and height while reducing depth. And this is exactly what was shown in the original paper on DCGAN. So here I am starting with these input noise vector, which is just a 100 element vector, also called the latent vector. And the generator starts with this vector, and using a fully connected layer, I reshape the vector into a 3-dimensional hidden layer with a small base, which is 4x4, and a larger depth, that is 512. Then using transposed convolution, the input is progressively reshaped such that its base grows while its depth decreases until I reach the final layer with the shape of the image that I am seeking to synthesize, which is 64 by 64 into 3. So if you actually, if I just open these output, that is the summary here in a separate text file, because here I'm getting output exceeds the size limit here. So this is the output from the summary. So here exactly you can see that I start with this 4 by 4 by 512. Then all these convolution, transposed convolution goes on. Here is one conv 2D transpose. Here is another. Here is another, and the last one is here. And at the last end of the last one, I get the final image shape that I want, which is 64 by 64 by 3. So my original 4 by 4 by 512 now becomes 64 by 64 by 3, which is the original dimension of Celeb A dataset as well. And that's what I am producing from my generator model. And after each of these transposed convolution layer, I am applying batch normalization and a leaky ReLU. So you can see here is one batch normalization and leaky ReLU, then leaky ReLU batch normalization, leaky ReLU batch normalization. And in the final layer, I no more apply a batch normalization, and also I no more apply a leaky. Instead, I give an activation of sigmoid. So the idea of the generator of DCGAN for Celeb A dataset is that by the end of the model, I want to decrease channels to 3 and increase the width and height to reach the original image size, which is 64 by 64. So what I'm doing here is increasing the first hidden layer, that is the dense layer, to project the data to 4 by 4 by 512, and then keep adjusting the filter for the subsequent layers, that is number of filters here. So I'm taking number of filters 256, 128, 64. I'm reducing it continuously with each conv transpose layer. And the final conv transpose layer, I'm giving these number of filters 3, so the final output will be 64 by 64 by 3. That is, in other words, the generator G needs to be designed to map the latent space vector, that is this 100 element noise shape, to the required data shape, which is 64 by 64 by 3 in this case. And since our data are images, converting these noise vector to data space means ultimately creating an RGB image with the same size as the training image. And this is accomplished through a series of strided two-dimensional convolutional transpose layer, each paired with a 2D batch norm layer and a ReLU activation. And if I were to do this project of applying DCGAN on MNIST dataset, for example, just an example, so the MNIST dataset is shaped as 28 by 28 by 1 because they are all grayscale. Then I would choose a dense layer at the beginning such that it takes a seed, that is this noise vector, as input, and then upsample continuously through various layers several times until I reach the desired image size by the end here, and the desired image size in the case of MNIST would have been 28 by 28 by 1. That pretty much wraps up this video, and all my upcoming videos will all be on some great computer vision projects and algorithm with Pytorch and TensorFlow. So stay tuned, and if you have not subscribed yet, do subscribe. And if you like this video, smash the like button. Thank you for watching.